We are beginning our FRQ topics review for the AP exam. An exciting time of the year for us, time when all of the information is put together for us, and we apply it in the way that we're going to need to for the AP exam. Okay, today we're doing area and volume FRQs. You see the recent years that we have seen this topic on the AP exam. It has been a popular topic lately, and almost always these are no calculator. Okay, you're going to be given a region defined by one or two functions. Okay, remember area is always the integral of the top minus the bottom if you get to do a dx, or right minus left if you're doing a dy. If you have to do a dy, make sure all of your curves are x equals something with y's in them. Okay, volumes. Okay, the general formula for volume, volume is equal to integrate the area function, the area of a cross section. Area of a cross section, dx or dy. Okay, your boundaries will be x values if you have a dx, y values if you have a dy. Okay, I apologize for my voice. I'm getting over a summer cold. I'm feeling really good, so hopefully I can make this video without annoying you too much with my gravelly voice. Okay, all right, so if you're given a cross section, shape, okay, S is the top minus the bottom, so there will be X's in that. Unless you have to do a dy, then there will be y's in that. All right. Squares, if your cross section is a square, then the area of the cross section will be s squared, because that's the formula for the area of a square. Equilateral triangle is square root of 3 over 4, s squared. Semicircle, pi over 8, s squared. Those are all area of the cross sections. I'm not going to go through all these because you can just read all of those. For a rectangle, one of the sides will be one of the dimensions of the rectangle, and for the other dimension, you'll have to use whatever information they give you. Okay? So just think. This is base times height, or length times width. Okay. If you have a region, if you have a solid that is formed by revolving a region around some sort of axis or some line, period, then you're going to set up a template. Okay, the easiest way I can think of to tell you this is it's a template. Pi big R squared minus pi little r squared, either dx or dy. If it's a dx, you're perpendicular to the x-axis. Each cross-section is perpendicular to the x-axis. If it's a dy, each cross-section is perpendicular to the y-axis. So for a dy, all of your axis of revolution will be vertical. For a dx, all of your axes of revolution will be horizontal. Okay? All right. And then we'll do a couple of examples on this. But length of a curve is this formula. Length of a curve. Integrate. This came from the Pythagorean theorem when we derived it back when I taught you this. This came from the Pythagorean theorem. So square root 1 plus the derivative squared. Okay. Let's jump in and do an example. So I'm going to start with the FRQ from 2014. Get a little sip. Okay. And I don't know why I don't have these. Oh, I should have these. Well, anyway, by the time you get them in class, I will have that filled out. Oh, I'm sorry. I know why I don't have them. 2014, I don't know what the KHS and the Texas average were then. I do know what the global average was. It was 4.5. Okay, let's take a look. Let R be the shaded region bounded by this curve and this line, and the vertical line x is equal to 1 as shown in the figure. So I know this is the exponential function, and this is the line, and this is a line. Part A, find the area of R. Area of R. So you'll have a box in your answer sheet that you will put all of your information in, and it'll be cordoned off for you. All right, so find the area of R. So everything that is in your answer has to be within the box provided for that part of the question. Okay, area. I think to myself, area is integral of top minus bottom if you have a dx. Right minus left if you have a dy. Here we have it. We can easily do top minus bottom no matter what the where we draw this line inside of the region. The same curve is always on top, the same line is always on the bottom. So we're doing top minus bottom. So I'm going to say it's the integral of the top curve minus the bottom curve dx. What are the boundaries? 0 is the lowest boundary, 1 is the highest boundary. So think of it as I'm starting over here at 0, and then I'm doing all of these little bitty tiny rectangles. So I'm starting at 0, I'm ending at 1. All right. Okay, so now it says find the area, so we actually have to work this out. We don't have a calculator, so we're going to work it out. Okay, I'm going to split this up into 2 pieces. Okay, for this piece I need to do a little u substitution. So I'm going to let u be x squared, du is 2x dx, 1/2 du is x dx. So this x dx is my 1/2 du. So this becomes the integral of 1/2 e to the u du. Okay, new boundaries. We need new boundaries here. My u boundary on top, I'm putting a 1 in for x, so the new upper boundary is 1. The lower boundary is still 0 because 0 squared is still 0. For this piece, I know how to integrate that. That is x squared, little power rule on that, from 0 to 1. And now I have 1/2 e to the u from 0 to 1 plus, over here I'll just have 1 minus 0, right? And over here I have 1/2 e to the 1 minus e to the 0. And I'm going to safe stop right there. That'll be good. Okay. Part B. So this would be within its own box, but I have just one big box for all of our answer. Okay, part B. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y is equal to -2. So here's the horizontal line, y is equal to -2. I know that they would never have me go through the region, so I know it's somewhere below, right? I believe as this turns out, it turns out to be right even with that, so I should have drawn it like right here. But regardless, it's right there. Okay. So this is a volume formed by revolving. So in my mind, I'll do it right here. In my mind, it's going to be integral pi big R squared minus pi little r squared. Dx, dy, this is going to be a dx because it's a horizontal, it's like the x-axis. Okay, so what is big R? It's always from your axis of revolution to the far side of your region. from the axis of revolution to the far side of your region. Okay? And then you do top minus bottom. So this is going to be x e to the x squared minus a -2, minus -2. Little r is from the axis of revolution to the close side of your region. You should only see white space when you draw your little r. This is big R, this is little r. Only white space. Top minus bottom, -2x minus -2. -2x minus -2. So I can write that down here in the box because they're not going to see it up there. Integral pi times x e to the x squared plus 2 squared minus pi times -2x plus 2 squared dx. Now I need some boundaries. My boundaries are still 0 to 1. That's it. Okay, part C. I think I'm going to put part C up here. Okay, write but do not evaluate an expression involving one or more integrals that gives the perimeter of R. The perimeter of R. Well, for the curve, the length of this curve here, we'll have the square integral 0 to 1, the square root of 1 plus, okay, I need the derivative of this squared. So I'm going to come off to the side. I'm writing what I'm doing. Remember, they're not going to read your mind. You have to write what you are doing. I'm taking the derivative of this thing. I need to use the product rule. Derivative of x is just 1, multiplied by e to the x squared left alone, plus, now we're leaving the x alone, and we're multiplying by the derivative of e to the x squared, which is 2x e to the x squared. So I'm going to have 2x times this x, e to the x squared. So that'll be that derivative. So e to the x squared plus 2x squared e to the x squared squared. And that gives the length of this piece. Okay. Now I need the length of this piece. So for the length of that piece, and I'm running out of room, I think I shouldn't have put this derivative right here. I think I'm going to come back here, come down here, rewrite it down here. Plus. Okay. Now for this piece, I think I'll just do a derivative, an integral for this one too. Still 0 to 1, square root, 1 plus. The derivative of that'll be easy, right? The derivative of this is just a -2, like that. Oops, sorry, can't see that. Okay, just like that. Plus, now we need the length of this vertical line. So what is the length of this vertical line? Well, the length of that vertical line is this y value minus this y value. It's top minus bottom. That y minus that y. What is this y? Well, that is when x is 1, we're at e to the 1, so that y value is e right there. This y value, when x is 1, this y value is -2. So, come down here, top minus bottom, e minus -2. And that'll be the perimeter. Okay? So I ended up not needing this up here, so I think I'm just going to cross it out. Don't bother erasing. Don't bother erasing if you don't want something to show, you just cross it out. Okay, how was this scored this year? Let's take a look. In part A, 1 point was awarded for the integrand. 1 point was awarded for setting it up, in essence, setting it up. 1 point was for the integrand. 1 point was for the antiderivative, doing the u sub and then the other piece. 1 point was for the final answer. For part B, that was right but don't evaluate. 2 points were awarded for the integral. They split that up, I'm sure, somehow, but we don't know how. 1 point was awarded for what they say, the limits and the constant. The constant is the pi, and the limits are the boundaries. And then for part C, 1 point was awarded for that derivative. Here's how they wrote the derivative, but it's the same thing that we had. 1 point was awarded for the integral. We had 2 integrals, but I think they're talking about this integral here. And then 1 point was for the answer, all the pieces together. So that's how that was scored that year. Okay, now we're going to take a look at the FRQ from 2021, the spinning toy problem. This year my students did not care for this problem, not even a little bit. You can see how they compared not only to the global average, but to the Texas average. It is very rare that we score lower than the Texas average. We occasionally will score lower than the global average, but not the Texas average. I guarantee I can count on one hand how many times we've scored below the Texas average on an FRQ. So my students did not like this. Now I will say, my students, this makes us look bad that year, but this was not a bad year for us. We'd scored really well overall on this exam this year. My students told me that they knew that this was a hard problem. They just didn't spend time on it. They went and spent their time wisely on problems that they could get lots of points on. And I absolutely am proud of them for doing that. Do not spin your wheels, no pun intended. Don't spin your wheels on a problem that you know is really hard and it's going to not award a whole lot of points, even if you try hard on it, even if you spend a lot of time. So, it's all good. Okay, let's read this. A company designs spinning toys using the family of functions where C is a positive constant. The figure shows the region in the first quadrant, bounded by the x-axis, and the graph for some C. Each spinning toy is in the shape of the solid generated when the region is revolved around the x-axis. So you can imagine this spinning around. It would become kind of a top shape, a spinning top shape. Okay, part A. Find the area of the region in the first quadrant, bounded by the x-axis and the graph. So what is this area? My students did not like that little guy right there. But in this one, they tell you the number for that. So that's okay. This was no calculator. One of the things my students said that they had a hard time with was knowing what this boundary was. Well, let's say in part A here, in part A, we know that y is equal to cx square root 4 minus x squared. And they tell me that c is 6 in this part. All right. Well, you guys, when x is 0, y is 0. What is the other value of x that makes y 0? The other y-intercept has to be 2, right? So this has to be 2. Not just in this part where c is 6, but for any c value, this has to be 2 out here. So what is the area? Integral 0 to 2, top minus bottom, but the bottom is 0, so it's just that curve. It's just that curve. So 6x square root 4 minus x squared dx. And we just need to find the value of this integral. So another u sub, u is equal to the inside of that square root. Du is negative 2x dx. Negative 1/2 du is x dx. So x dx is negative 1/2 du. I'm going to take the 6 out, and I'm going to write the negative 1/2 out. Negative 1/2 times 6 is negative 3. So that's the 6 and the negative 1/2. And then inside I'm going to have u to the 1/2 du, because that's square root. What is my new upper boundary? If I put a 2 in for x, I get 4 minus 4, which is 0, so my new upper boundary is 0. If I put a 0 in for x, I get 4 minus 0, which is 4, so my new lower boundary is 4. I need to reverse those because I have the larger boundary on top, so it's going to change it back to a positive 3, or it's going to change it to a positive 3. And now I can integrate. Okay, add 1 to your power, divide by your new power. Still got the 3 outside. From 0 to 4. These are u values, right? So leave them as u values. Okay, let's see. These 3's are going to cancel out, so I have 2 times 4 to the 3/2 minus 0 to the 3/2. I'm going to safe stop right there. Of course, you don't have to write 0 to the 3/2, but I'm safe stopping right there. Okay, that's part A. Okay, let's come over here and do part B. Okay, part B. It is known that this function has derivative this, so they're giving us the derivative. They're making us not have to do the derivative. For a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. What is the value of C? Okay, this spinning toy, I'm going to sketch it so you get an idea of what's going on. This spinning toy. Okay, can you kind of see it? See that cross-sectional, that, like that. That's what it's looking like, okay? Okay, it says the radius of the largest cross-section. It would be somewhere around here, right? This radius. This radius is 1.2 inches. Okay, what's happening right there? What's happening right at this spot? Well, at this spot, the slope is 0, right? That's the key to this part of the problem. Okay, they gave me the dy dx. I need to set that equal to 0. And they tell me that when that slope is 0, the radius is, r is 1.2, right? So that means the y value is 1.2. Okay, so I'm going to write what I'm thinking. I'm finding when that slope is 0, and that will happen when y is 1.2. That's the height there, the radius, that's the height. Okay? All right, so that's my go-to. So I'm going to take my my dy dx and set it equal to 0. So c times 4 okay. Solving this for x. Yeah? I don't know what c is, but I know it's not 0, right? I know it's not 0 because they tell me it's not, it has to be positive. So c is not 0. So what would make this thing 0? Well, what would make this thing 0 is when the numerator here is 0. So this is 0 when 4 minus 2x squared is 0. Not the denominator, the numerator. The numerator has to be 0. So this is when, let's see, negative 2x squared is negative 4, x squared is 2, x is the square root of 2. So now I know that at this spot, x is square root of 2. X is square root of 2. So now I need to find y. Well, there's my function for y. Okay, so, and I know that y is 1.2. Y is 1.2. I don't know what c is, but I know what x is. The square root of 2 squared is 2. Okay, I need to solve that for c. We're asked to find the value of c. Now it gets super easy. Got 1.2 is equal to c times square root of 2 times square root of 2 is 2. So c is 1.2 over 2.6. But I'm going to say stop right there. That was the value of c. All right, part C. For another spinning toy, the volume is 2 pi cubic inches. What is the value of c? So volume of a solid formed by revolution, right? So remember, integral pi big R squared minus pi little r squared dx. They tell me that that has to equal 2 pi. I'm writing it up here just for scratch work. I'm not going to write that down where I'm putting my answer. But that's my thought process. Okay? Now, my axis of revolution is the x-axis. So top minus bottom is just that curve, right? It's just that curve. And there is no little r. Little r is just 0. So this will just be a 0 here, and this will be my y there that they gave me. So I will have the integral 0 to 2 of pi times cx square root 4 minus x squared squared. Pi r squared minus 0 dx. And that must equal 2 pi because they told me it. Okay, I'm going to solve this for c because they asked me to find c. All right, so c is a constant here. C is a constant. So there's a c here. I'm taking the integral with respect to x. That's a constant. So I'm going to take out the pi. I'm taking out the pi. There's also a pi over here. So when I take out the pi, I can reduce it with the pi over here, and then those pi's are gone. I'm going to square this product in here. This will be c squared, x squared. The square root squared will be that. And that's equal to 2. C squared is a constant, so I'm taking it out. What's left, I'm going to distribute like that. I'm getting closer. I'm going to leave the c squared out here. Integrate. So 4/3 x cubed minus 1/5 x to the 5th from 0 to 2. Just keep everything straight. We're doing fine. Put 2 in for your x. This is 8. 8 times 4 is 32. Or you can leave it, right, and save stop. 2 to the 5th is 32, but we're dividing by 5, so 32 over 5. And then when you put in 0, that'll just be 0. So c squared is equal to 2 divided by this thing. I'm going to be safe stopping here, so I'm just going to write it. And then I take the square root of both sides. A mess, but it's correct. Okay. How was this scored? It's a tough problem, huh? Tough problem. How was it scored? Well, for part A, 1 point for the integrand. Oh. 1 point for the integrand here. 1 point for the antiderivative. 1 point for the answer. So that was worth 3 points. Part B, over here, 1 point was awarded for just setting dy dx equal to 0. And then 1 point was for the answer. So that part was just worth 2 points. Part C. Part C was clearly worth 4 points because every FRQ is worth 9 points. 1 point was for the form of the integrand. I'm assuming it's like pi r squared. 1 point was for the limits and the constant. Did you use the right boundaries? 1 point was for the antiderivative. 1 point was for the answer. 4 points. Okay, I did 2. You do 3. Okay, good luck. Always do these. I'm only assigning 3. 3 problems. So always do these.